We've seen in our class already that different samples give different results, and this fact is called sampling variability. A new term is sampling distribution, which is a collection of outcomes calculated with all possible samples of a certain size. Whenever you pick a certain statistic, like a mean, a median, or a mode, and you calculate that value with all possible samples, you get a sampling distribution. So if I calculate the mean of every possible sample, I get a sampling distribution of means. If I calculate the median of every possible sample, I get a sampling distribution of medians. The most basic type of sampling distribution is a sampling distribution of means, which is what we'll talk about in this video. Here's a demonstration. So let's imagine that this is a population of 72 students, and maybe they're the students in a certain class, and each student has his or her own exam score. So what if we wanted to look at a sampling distribution for all possible samples of 3 people? What we would have to do is actually calculate the mean of every possible sample of 3 people. So here's one possible sample of 3. If you add their 3 scores and divide by 3, you get their mean, and it's right there. These 3 in the brown circles are a different possible sample. If you add their 3 scores and divide by 3, you get the mean of those 3 people, which is 74. Their sample mean is right there. So these 3 people in red have a higher average, mostly because of this A student and this B student. These 3 students are all have C's, so their average is in the 70s. Here's a different possible sample. It overlaps the brown sample, but since it's not the same exact sample, it is a different sample. So it's a different possible sample of 3 people, and it has its own average. That's the mean of the blue sample. The green sample overlaps the blue sample, but it's still a different possible sample. If you add their 3 scores and divide by 3, that's their sample mean. And if we kept, if we did this for all possible samples of 3 people and kept going, and we kept plotting the mean of each possible sample, we would get a sampling distribution for the means of all possible samples of 3 people. So these sample means are building up to form the sampling distribution for all possible samples of 3 people. And if we actually did calculate the mean of every possible sample, we would probably see most of them piling up in the middle and fewer of them down here and fewer of them up here, because these samples down here would be more extreme and these ones up here would be more extreme. So if we wanted to calculate a sampling distribution for a sample size of 10, we would have to calculate the mean of all possible samples of 10, meaning all possible combinations of 10. So there's one combination. If you add their scores and divide by 10, you get the mean of that sample. The green one is a different possible sample. Their mean is right there. The blue is a different one. Their mean is right there. So here's some different means of some different possible samples. Notice how the means of these samples of 10 people in here are piling up more closer to each other and closer to 80, which I think is the mean of the class, actually, because when you look at the means of larger samples, the sample means are closer together, and they're also closer to the mean of the population. So if you added all 72 scores and divided the total by 72, you would get this population mean of 80. Each of these sample means is just estimating the population mean of 80. So now let's talk about the shape of a sampling distribution. According to this rule right here, if the population is normal, sampling distribution is normal, meaning if you if these individual exam scores follow a normal curve, then this sampling distribution of means will also end up forming a normal curve. No matter what sample size the sampling distribution is based on. So if this population is normal, then this other sampling distribution back here, with all possible samples of 3, would follow a normal curve. And this sampling distribution for all possible samples of 10 would also follow a normal curve. It would build up to a normal curve. So if the population is normal, the sampling distribution is always normal. But if the population is skewed, the sampling distribution is skewed just like the population. If you're selecting small samples, but will be roughly normal if you're selecting large samples, such as samples of 30 or larger. So if the population is normal, and you take a certain sample size, the possible samples will always follow a normal curve, regardless of what sample size you're dealing with. So, for example, if I know that a certain population, like San Jose, is normal, and then, for example, if I know that the heights of people in San Jose follow a normal curve, and I take all possible samples of 10, and I calculate the mean of each possible sample, the sample means will follow a normal curve. If I take all possible samples of 20 and calculate the mean of each one, those means will follow a normal curve. Or if I do it with the sample size of 30, it'll be a normal curve. The sample size doesn't matter. Here, if the heights of people in San Jose are skewed, and I calculated the mean of all possible samples of 10, those sample means would be skewed just like the population, because the sample size is small. 10 is less than 30. But if I calculated the mean of all possible samples of 30 from San Jose, the sample means would end up, all of those sample means would end up being at least roughly normal, even though the population is skewed. So to help us understand this idea of a sampling distribution, let's look at how it would be created with a small population of 4 people. So here we have a population of 4 people. Let's maybe say that this is the height of each person in the population, and I want to take a sample of 2 people from this population, and I want to calculate the mean of my sample by adding the 2 heights and dividing the total by 2. And I'm going to use the mean of my sample to estimate the mean of the entire population. Now, if I do that, what are some possible samples of 2 people? Well, I could get person 1 and person 2. I could get 1 and 3. I could get 1 and 4, right here. Or I could get 2 and 3, 2 and 4, and 3 and 4. Those are the 6 possible samples that I could end up selecting if I take 2 people from this population. If I end up getting this sample, my sample mean will end up being this, because if you add these 2 numbers and divide by 2, it comes out to 55. But if person 1 and person 3 ends up being my sample mean will be 56. And if I end up getting sample 3, this will be my sample mean. So every possible sample has its own sample mean. So if I take a sample of 2 people and I calculate the mean of the sample, I'm going to get one of these 6 possible outcomes, because I'm definitely going to get one of these 6 samples right here. And the number that my sample mean comes out to depends on which of the 6 samples I end up selecting. Now, if I decided to take a sample of 3 people from the population and calculate the mean of my sample, then these would be the possible samples. I might get 1, 2, and 3, 1, 2, and 4, 1, 3, and 4, or 2, 3, and 4. Each time I wrote one of these out, I just left out a certain person. This leaves out person 4, this leaves out person 3, this leaves out 2, this leaves out 1. So these are the 4 possible samples of 3. So, and if you add these 3 numbers and divide by 3, that's the mean of that sample. The same thing here. So if I take 3 people, I record their heights, and I calculate the mean of the sample, I'm going to get one of these 4 possible outcomes. And this right here just lists out the mean of each possible sample. For example, if I get sample 2, that's my sample mean. If I get sample 2, that's my sample mean. Now let's talk about how the mean of the sampling distribution is always equal to the mean of the population. So if you want the population mean, you add the 4 individual heights in the population and divide the total by 4. That's the mean of the population. We can see it's at the center of the population. The symbol for population mean is this symbol right there. X bar is sample mean. Now, if you want the mean of the sampling distribution for all possible samples of 2, you could add these 6 numbers and divide the total by 6, and it comes out to the population mean. So the center point of the possible samples is at the population mean, meaning we have the center point of 57. The 3 samples above it have sample means that overestimate the population mean. The 3 samples below it, below 57, have sample means that underestimate the population mean. But we can see that half of them overestimate, half underestimate, because the center point is the population mean. The symbol for the mean of the sampling distribution is mu with an X bar at the end, a subscript, saying the mean of the sample means. Here we can see the 4 population members. Here we can see the 6 sample means of all possible samples. And we can also see that this is the mean of the population at the center. This is the mean of the mean of the 6 sample means of 57 is also at the center point of the possible samples. I said that these underestimate, these overestimate. Now if we added these 4 sample means of all possible samples of 3 and divided the total by 4, we would get 57. So once again, the population mean is at the center of the possible samples. These 2 samples have sample means that underestimate. These 2 samples have sample means that overestimate. But the population mean is still at the center. Notice how this time the sample means are more closely packed in toward the population mean of 57. So overall, the sample means are more accurate with the larger sample size, meaning if I take a sample of 3 people from this population, I'm likely to get a more accurate sample mean than I would have if I had taken a sample of 2. Here we can see it right here. They're all pretty close to 57. So here we see the 4 population members are the most spread out. The means of the possible samples of 2 are closer together, and the means of the samples of 3 are the closest, because we're going from a sample size of 1 to a sample size of 2 to a sample size of 3. So they all have the same mean. They're all 3 of these are centered at 57, but they don't have the same dispersion. That's the highest, that's lower, that's the lowest. Sorry, this got stuck for a second. That's the lowest. So the standard deviation of a sampling distribution is called a standard error. So the standard deviation of these four numbers is called the population standard deviation because it's the standard deviation of the individual people in the population. The standard error of these six numbers in here, the standard deviation of the six numbers in here would be called the standard error because it's the standard deviation of a sampling distribution. So if we calculated the standard deviation of these four numbers, it would be called the population standard deviation. If we calculated the standard deviation of these six numbers, it would be called the standard error, even though both of them are really just standard deviations. Because all a standard error is the standard deviation of a sampling distribution. If we calculated the standard deviation of these four numbers, it would also be called a standard error because it would be the standard deviation of a sampling distribution. So that's what the standard error is. The standard error measures how spread out the sample means are from each other. So you could probably already tell that this would have a higher standard error, this would have a lower standard error, because these are more spread out. So when the sample means are more spread out and they're less accurate overall, the standard error is bigger. When the sample means are closer together and more accurate, it's a smaller standard error. Now, how can the standard error be calculated? Well, if we actually know the mean of each possible sample, we could just plug the six sample means into the standard deviation formula, like this. And remember how back when we talked about the standard deviation, we said that you divide by n if it's a population and n minus 1 if it's a sample? We're actually using n because these numbers aren't the numbers inside of these four numbers aren't actually, these six numbers aren't actually a sample. They're the means of all possible samples of 2, which means that they're actually a sampling distribution. So if it's a sampling distribution, you actually divide by n. So not n minus 1, because you can think about it this way. It's actually, what this actually is it's actually an entire population of sample means, because we're looking at the means of every possible sample of 2. Because these are all 6 possible samples. No samples are being left out, which means that this is kind of like a population of samples, I guess, which would mean that you would use n instead of n minus 1. So it comes out to 1.29 once you go through all these steps to divide and then get the square root at the end. This would be called a standard error because it's the standard deviation of the sampling distribution. So if we go back up here, so if I calculate the standard deviation of the 4 people in the population, I use n instead of n minus 1 because it's an entire population. If I calculate the standard deviation of the people inside of a certain sample, like these 2 numbers right here, I would use n minus 1 because these 2 numbers are a sample. If I calculate the standard deviation of these numbers over here, of the sampling distribution, I divide by n, because this can be thought of as actually a population of its own. So it's a population of samples. So this would be n, this n minus 1, this n. Now if I wanted to calculate the standard error of all possible samples of 3, I would take these 4 sample means that we calculated earlier and plug them into the standard deviation formula. Once again, I'm using n instead of n minus 1. I total the squared deviations. I divide by n, which is 4, because there's 4 of them, and I get this number. It's the variance, and the square root of it is the standard deviation. And it's actually called the standard error because it's the standard deviation of the sampling distribution. And we can see that it comes out to a smaller number with the bigger sample size, because when I did it with all of the samples of 2 back here, it was 1.29. Here it comes out to 0.7, a smaller number, because here the sample means are more accurate and they're closer together, so they're less spread out, which means a smaller standard error. It's also possible to calculate the standard error with this shortcut formula right here. This sigma is the population standard deviation. This n is the sample size. This capital N is the population size. So let's see how this works. If we want to use the formula, we have to know what the population standard deviation is, because that has to go in here. So we have to calculate the standard deviation of the population, then we can use that formula. So here we go. What if we have this population right here of 4 people, and I record the heights. I take a sample of 2, I record their heights, and I calculate the mean of my sample. I want to know what the standard error is of all of the possible samples of 2. Well, the population standard deviation would just be calculated this way, using this formula we talked about before, and it comes out to 2.24. Once we have the population standard deviation of 2.24, going through all these steps, what we can do is take that and plug it in here. So take the 2.24, which I found, plug it in here. The sample size is 2. Remember, I'm taking a sample of 2 people from the population. I said that in the question. I'm taking a sample of 2 people from a population of 4 people, which means that sample size is 2, population size is 4. And this was the population standard deviation. If I can simplify by subtracting and subtracting. I divide 2 over 3 to get this number. And then I just take the square root and it comes out to 0.82. After that, I can also take the square root of 2, which is 1.41. I divide this fraction, this by this, and I can get 1.59. I multiply and I get that answer, 1.3. And over here, when I got the population standard deviation, all I did was I calculated the standard deviation of the 4 people, of their 4 individual numbers. That's why it says person 1 and person 2 instead of sample 1 and sample 2 like it did before. What if I have the same population and I'm taking a sample of 3 and I want to know the standard error of the possible samples? In other words, I want to know the standard deviation of the means of all combinations of 3. Well, I can calculate, I just need the population standard deviation again. It's still 2.24 because the population hasn't changed. The only thing that's going to change this time is the sample size. I'm now taking a sample of 3 from the population of 4, so the little n will be 3, the big N will still be 4, because that's still the population size, and the population standard deviation is still 2.24. I get 0.7. And now I want to show you a summary of this. doing this, calculating the standard error both the long way and the short way. So here's the population. Here's their four numbers, their four data values. Here's the standard deviation of 2.24 calculated this way. If you want to do it if you want to get the standard error for the sample size of 2 the long way, you could actually calculate the means of all possible samples of 2 people, and list them out here, and then calculate the standard deviation of this list going through these steps and get the answer of 1.3. That's the standard error. But you could also take the population standard deviation of 2.24, plug it into the standard error formula with the sample size of 2 and the population size of 4 and 2 right here, and get the same answer. These are both the standard error. If I want to get the standard error for the sample size of 3 the long way, I could calculate the means of all possible samples of 3 one at a time and get these 4 sample means, and then calculate the standard deviation of the list and get 0.7. Or I could just plug in my population standard deviation right here, my population size of 4, because it's 4 people, and my sample size of 3. And I get the standard error of 0.7, which is just the standard, this is just the standard deviation of the means of all possible samples of 3 people. So this right here is a standard deviation of the means of all possible samples of 2 people that could be selected. This right here is the standard deviation of the means of all possible samples of 3 people that could be selected, and they're both called standard errors. So this is the same thing as this is the same thing as this.